We said we were going to do that, try to keep up with that. Before we get started in chapter 3, I'd like to ask if anybody has any particular questions about chapter 2 from the homework or anything like that. Everybody doing okay? Did the chapter 2 homework go fine? Pretty simple, straightforward stuff. I think so. All right. So we're going to get on with things in chapter 3. If you do have questions about chapter 2, feel free to email me or send me a message through MATLAB. Either way works fine. Today we're gonna learn about MATLAB's built-in functions. And what's important to realize when you're programming is that programs are not the end-all of computers. Things like MATLAB, Microsoft Word, Windows. Beneath every one of those programs is another program running that program, and another program running that program, and another it's just layers and layers and layers of depth to the programs running on a computer until you finally get down to what is called the machine language. And the machine language is literally charged transistors and uncharged transistors. You have these little things in the computer that either have a voltage on them or do not. And when they have a voltage on them, that's equal to like a 1 rather, and when it's not a voltage, it's equal as a 0. And so that at that level, it's just all binary code numbers. It's just binary numbers, 0 and 1. And so whenever you ask a program to do something, there's always some kind of code behind it. In MATLAB, I believe the kernel code, the code that you've written the program in to make a new program is usually called the kernel, right? And I believe that the kernel of MATLAB is C+ or something similar to that. I don't know exactly. C+ is another language, and there are many languages out there, but it's not as developed as MATLAB. So MATLAB is considered a higher developed language or a higher level language. And with higher level languages, you have easier program, better interface, more usability, user friendliness kind of thing going on. And it's usually much quicker to write your code. But when you're done, your code has a tendency to be much less efficient because of all the underlying code underneath it, right? And code that is lower level code, lower languages are much more efficient. You can write code in those very efficiently, but it takes a long time to do it usually to the level, to get the same results as you would from a higher level language. Just because you don't have all the built-in kind of stuff in the background that is kind of in. So when we this last chapter, when we did something like one of the things we did, like when you did x squared, so you said x equals 9, even just behind this thing, behind the x, there's code that tells this computer what that is. Tells it, well, first of all, it's a character, not a number. And then when we type a character into MATLAB like this, we're supposed to recognize that as a variable. And then when we put an equals sign next to it, that's supposed to be and there's code for all this. It knows what to do with each of these characters, and it goes ahead and does it. Oops. So it goes ahead and does this. By the way, if you don't want something to print out to your screen, I just did that on accident. Instead of writing x equals 9 and just hitting enter so it prints to the screen, you can write x equals 9 with a semicolon and it won't print to the screen, but it still creates the variable over here. So it's still there. Yep.
Video participation, you took it off, but I didn't upload it because it's on that the laptop that you gave me, not my laptop.
For your what?
The video participation.
Oh yeah, I can get that back for you. I don't know where I put. Oh, it's right there. Yeah, yeah, you can grab that and pull it off there. Here's an SD card you can pull it off with, unless you want to just put it up online directly from there. That's one too. Yeah. But So anyway, so these layers of code become quite important. So if I want to do x squared, for example, there's a whole bunch of stuff in MATLAB that knows how to do that. So what it does is it sends this command to that little piece of code that's built into MATLAB, and it does the calculation, and it spits it back out, and it prints it to the screen, and you're done, right? Or even if I just put this semicolon here, or the semicolon here, MATLAB has an entire routine of code written to put in that semicolon. And of course, the code that MATLAB's written in has some code for doing some things. And it's just this layer upon layer upon layer of code. And this is actually why we have so much problem with computer code these days. You know, you get a new version of whatever, get a new version of your Apple, of your phone software or something, right? Well, all that they're doing is writing code to fix problems with the previous code, usually, right? The best way, the good way to do that, if you're a really good programmer, is to start over with your code and fix the code from the lowest level possible, so that you're not building bad code on top of bad code and then code to fix the bad code on top of bad code, and so on and so forth. And when you're talking with computer people, they usually call that bloatware, where this software is just getting bloated. It's getting fatter and fatter with all these layers of corrections and layers of changes. And they call it bloatware. And actually that word was actually invented to describe Windows, Microsoft Windows software, because Windows software is easily the worst example of bloatware ever to be invented. I believe that Windows is still actually using the same kernel that they used in 1995. And they've been using that same kernel since. They tried to change it, but they didn't put the work into it that they needed to. And that was in 2000, they tried to change it, and it just completely bombed. And so they just went back to the 95 kernel that was pretty stable. And it's fine as long as people are in there fixing the underlying code and going into the lower levels, but they didn't do that for the longest time. And I don't know if they've done it lately. I haven't really been keeping up on it. But Windows was notorious for this. Bill Gates was all about making money and not about fixing his code when he was running the company. He doesn't run the company anymore, and so I think they've changed that. I think Windows is much more stable than it used to be. But still, it's pretty common to log onto a Windows computer and have 30 minutes of updates, right? Those 30 minutes of updates are fixes to mistakes in lower levels of code. And they're not going in and changing the code, they're just writing code on top of it. And so you need constant updates and revisions. And you can't avoid updates and revisions in code. It's just a fact of life. But if you're a good programmer, every once in a while you go in and you tear it down a few layers of code and start fresh. That's a good way to program, because then you can get rid of a bunch of junk and start fresh and make it right. Use the mistakes you made over here to make a better one here. And it's a lot of work and it costs a lot of money, but it's worth it. And frankly, that's actually the difference between between what we term the Mac and the Windows world. Mac has spent a lot of time rebuilding their code, and Linux is another type of code that's an open source code that does the same thing. They've spent a lot of time trying to rebuild their code. And Linux and Mac are actually written on the same kernel. They're written on Unix, which is the most stable platform ever created for computers. So that's the reason there's like this big divide in computers. There are people that really swear by Windows, and there are people that really swear by Macs. And it comes down to really your philosophy in computers. If you have a philosophy of just push on and get it done, Windows is usually your computer, and it fits your style, and it's totally fine. It doesn't matter what you choose. But if you're a person that wants to just break down and rebuild it and rebuild it from the bottom up, then you're a Mac guy. And the other difference is price, because it's much cheaper to do it the Windows way. And so Windows is much cheaper. You can buy a Windows computer for $300 and it's fine. But Mac, you have to pay for those software revisions. And so you're paying for the same computer, the Windows computer, you're going to pay 3 times as much for a Mac because of the software that you're running on. And just because it's more stable. And I mean, you pay for it either way, one way or the other. You either pay the extra money or you pay for it in time doing updates, right? And of course, the architecture is a little bit different. People who are used to using Macs don't like Windows because it's a completely different interface now. They've kind of gone different directions. When you first had Windows and Mac back in 1980, when did the Windows come out? 82 or something, 84 or something like that, 86 maybe. But anyway, sometime in the mid 80s, Windows and Mac side by side were almost identical. You could really not tell the difference. There was a little difference in shape and color, but the way they worked was pretty much the same, but they've kind of gone in different directions. And so it's created this kind of social divide in, just getting used to the platform. But the underlying programming issues are also a huge divide. And it's not one is good and the other bad, or one is smart and the other is dumb, or whatever it is, because everybody always says that. Everybody says, well, Mac users are snobs, or Windows users are smart because they can, fix their own computers or whatever. There's no real difference as far as those things go. You can do anything on either computer pretty much equally well. They're both very capable computers. You have to do different things on each computer to do things. A lot of people like to say, well, Windows is much more customizable than Mac, and that's just not true. A lot of people like to say that Mac, runs video and animations much better than Windows, and that's just not true either. Neither of those things are true. They're just both computers, and once you learn how to work with the computers and work with those higher languages and get down to the lower languages, then you're fine. Because with each computer, with the Windows computer or a Mac, you can actually get into the lower level languages, and you can actually mess with the computer at a deeper level. On the Mac, it's called the terminal. That's the interface where you do that. Can't remember what they call it on the Windows computer, but it's essentially a little screen that allows you to communicate with the BIOS on the computer. So I mean, you can do anything with either computer. It really is mostly a philosophy thing, what your particular philosophy is. And you'll find that the people that deal with computers on the very low levels could care less about Windows or Mac, because they're not dealing with either of those programs. They're dealing with this stuff way down low that is pretty much the same across every computer on the planet. And so they don't care what's on the other end. They don't care what's high up there. They're just, typing away in languages that hardly anybody knows anymore. So the reason that I mentioned this is we're actually now going to learn something about some of these functions that are programmed already into MATLAB. We're going to learn how to use them, but we're also going to kind of learn a little bit how they're made and how they're created, because we're going to start to create our own eventually. And that's really when you become a programmer. You become a programmer when you create a program in a language that does something for you. So it behaves like another on the higher level program. And MATLAB can do that. MATLAB can create programs that do something else that are higher level programs. And surprisingly enough, you can actually do that in other programs, like you can do it in Microsoft Word. It's actually doable. It's not easy. You can do it in Excel. It's much easier in Excel. You can create a higher level program using Microsoft Excel. And an example of that would be my brother, who works for the Department of Energy. He actually created a program in Excel that tracks all of the energy usage and energy creation of natural resources like coal and oil and solar and all these things. And it tracks all of these things as they're being used and developed, I guess. I mean, when we mine the coal and when we burn the coal, or when we pump the oil, or we put up these wind farms, whatever. He tracks all of that energy and where it goes in different parts of the economy. And it's kind of interesting. I can show you the output of it. I don't know if I actually did show you this already, but I'll show it again anyway. I may have. So this is what it looks like, the end result of this program. There's several different versions of it, because you can do it and show it in several ways. But here are your inputs to the energy, the outputs, and all the pathways that it takes, and it has all kinds of numbers involved in it. This is the action one from the lab where he works, Lawrence Livermore National Laboratories. And Excel and the tracking is not something you have to type in. You don't have to go look up how much coal has been mined and how much coal is being burned in the country. The computer program does that. The computer program actually goes out and is always tracking that information. So this chart is changing constantly every minute of every day as to where the energy is going. And of course, for the Department of Energy, that turns out to be an important thing to keep an eye on. You need to know what's going on out there. So anyway, my brother is kind of an Excel guru, so he likes programming in Excel. I do not like programming in Excel. I'm learning more about it though. So let's learn about some of these built-in functions, these built-in like mini programs that are already built into MATLAB so that we can call them and we can use them at any time we need them. Make sure that you remember to start up your MATLAB so that you can work along with me, and unless you're going to do it later after the video is posted. So we're gonna start with a very simple one. We're going to go ahead and define some value. We already defined x equals 9, which actually is what they defined. That's good. And we're going to say that the variable b now, or this b here, is going to equal the square root of x. And of course, it knows how to do that function. It knows how to it can even do this one. Let's change x to -9. And we can even do b equals square root of x with -9. And it actually knows how to take the square root of a negative number. And when you take the square root of a negative number, you get a complex number. In this particular case, you get there's no real solution to this, but there is an imaginary solution, 3 times I, where I is the square root of -1. Right?
Jared.
Yes.
Can you share your screen with me?
Oh yeah, sorry. My bad. Where do I do that? Here we go. Okay, here you go. Sorry about that. All right. You can also do this with an array of numbers. So let's define x to be the array of, whoops, I'm not in my thing here apparently. X equals an array of numbers, and they're doing 4, 9, and 16, the first 3 squares besides 1, right? 2, 3, and 4, 2, 3, and 16. And that's now our x. We've changed x from a 1 by 1 array to a 1 by 3 array, and we're going to do b is equal to the square root of x again. 2, 3, 4. So it does each one of them all at one time. And of course, it stores that answer here in an array up here, where that array is the array 2, 3, 4, right? Remember that if we do something like this, where instead of having an array where we have 1 row and 3 columns, we do 1 column and 3 rows. It looks a little bit different, and we can do the square root of that as well. And then b will no longer be a 1 row, 3 columns. It'll be 3 rows, 1 column, right? It'll be 3 by 1 instead of 1 by 3. So that is also doable. So there you go. Your very first built-in function that is kind of obvious. The functions that are not obvious, we don't really call them functions. We usually call them operators, like the equal sign and the square sign and the multiplying sign. We usually call those operators, but they are actually little functions. MATLAB has to know how to do those things, but it turns out that we didn't have to write those in MATLAB usually, because they're written in the kernel of MATLAB. So we don't really have to rewrite them in MATLAB. And even the square root, pretty much every program in the world uses this command for square root. So you're not likely to have to reprogram this one. But functions often, we often differentiate the idea of operators that you use in a program, like the times sign and the minus sign and the plus sign, these things. We usually differentiate those from functions, where functions are usually something that you have to put something into. So you usually have parentheses or brackets, and then you have to insert something into that function, and then it spits something out. That's not always the case, but it is often the case with functions in programs. So here's another function that we have. I'm going to do, this is called the remainder function. The remainder function is a function that takes the first number that you enter into it, and it divides it by the second number that you enter into it, and then it spits out the remainder of that division problem. So if I hit this, it tells me the remainder is 1. And that can be useful because when you do division normally, like in a calculator, you get 10 divided by 3, and it gives you this answer. And then you're like, well, that means that 3 goes into 10 3 times, but there's something left over. I don't know exactly what it is. And for 10, it's easy, but it's not so easy for this one. Right? That one is difficult to do. So if you need to know the remainder after you've put 3 into something, and why would you need to know that? Well, if you're selling donuts, right? If you're selling donuts and you make this many donuts in a morning, and you want to know how many baker's dozen there are in there, you do this, and there happens to be, well, you want to know how many donuts you're gonna have left over after a baker's dozen, you have that. It's 3 donuts left over after a baker's dozen. So then all of a sudden you know that you don't want to make that many donuts. You want to make 10,000 or 103,000. That's a lot of donuts. 454 donuts instead. Then you'll have a nice even number of baker's dozens. And doesn't everybody do that problem every day in their life? Okay, let's look at a different one. Here's another one. This is a function built into MATLAB, and it's called size. The size function will return the size of a matrix. So we've got a couple of matrices in here. Let's do B here. Right here. So the size tells you the number of rows first, and then the number of columns next. So it turns out that B is a 3 by 1 matrix, 3 rows, 1 column. Okay. And you can actually do something interesting with this. We're going to learn how to assign 2 variables at once. So I could say that I'm going to just call this thing rows underscore and columns. So this tells me my rows and columns, and I'm going to name it rows and columns. So that equals size of B, right? Oops, size of B here. So rows and columns equals 3 and 1, right? Or I can actually do it this way. Instead of saying rows and columns equals size of B, I know that B has rows and columns, so I know that I'm going to get 2 answers out. So what I can do is I can actually separate rows and columns with a comma, and I can assign 2 different variables at once. I'm going to assign the variable rows to be the first number that comes out, and the variable columns to be the second number that comes out. If I put them in square brackets, rows, comma, columns, then the first number that comes out of this function is going to be called rows, and the second number that comes out of this function is going to be called columns, and that's what MATLAB is going to remember them as. So I go ahead and push return here, and it says, look, rows equals 3, columns equals 1. And up here, if you open up rows, which it made, it has 3 in it, right? If I open up columns, it has 1 in it. So it created 2 different variables, one called rows, one called columns, as the output of this function, size function. You can also have nested functions. We're at the bottom of page 63 if you're lost or anything. So here we have G equals, and I'm going to put a function inside of a function. So the first function I'm going to do, which is actually the last function that will be done, will be actually executed, is the square root. But inside of this, I'm actually going to take the sign of our variable x, which is still up here. It's that row, that column, that 3 rows, 1 column variable. So what this will do is it will do the innermost function first. It will do the sine of x first, and then it will take the square root of that answer next. When you do that, this is what you get. Now remember, x was 4, 9, 16, right? So we took the sine of these numbers as if they are radians, and then we took the square root, and it turns out that all of those turned out to be negative. One of them turned out to be complex. So we ended up with these i's here. It might be a little more illustrative for me to redefine x really quick. Let's do x, oops. If I redefine x as x equals pi, for example, then I can do the square root of the sine of x now, and that gives me this number because sine of pi, right? And if you go on your unit circle all the way around to pi, the sine of pi is 0, and the square root of 0 is even more 0, and so this is a very tiny number. Which is pretty much 0. Oh, square root of sine, so they're just doing some more things here. That's fine. Sine squared A, more nested functions. Okay, good. So those are some of our built-in functions, and there are lots of them. So we want you to know how to figure out how to use them. So how do we figure out how to use them? We teach you a new little trick here. Built into MATLAB is the help function. Now the help function doesn't require that you put any parentheses after it. You just need to put the name of a function after it. So if I do sine, for example, notice that it's in purple. That means that MATLAB is recognizing this as something that it can search for. If I put in sine, S-I-N-E, oh, it still does that, I guess, apparently. Maybe it'll do anything. Oh, it looks like it'll do anything. It used to only highlight it if it recognized it. If it didn't highlight it, but now it just highlights anything. So you can search for anything in here. But if you search for a function that it already knows and uses, and hit enter, it gives you a little short synopsis of how to use sine, or what it's used for. Sine x is the sine of elements in x. And then they say you can also look up the a sine, the sine d, the sine pi. And then you can actually push this button or any of these buttons, or not these links, I guess, they're not buttons, but anyway, these links to go to the actual help page in MATLAB. So it gives you a lot more information. It gives you examples on how to use it and how to plot it and all kinds of things in here. And this is great. Why? Because this is exactly what programmers want. They want to copy this right here, and they want to paste it right here, and then they want to hit return and see it happen, right? That's programming 101 in the 2021 year, right? Copy and paste your programming. I highly recommend you get used to doing that because it can save you a lot of time. And then you can go back and figure out what it's doing, how it works, you know. It's good to write your own code to learn how to do it, but it's also good to copy someone else's code and figure out how they did it. So that's the help feature. You can use it for just about anything. If you do help Jared, for example, it doesn't have anything in the documentation for MATLAB. Or if you do help, where's my help sign? There it is. If I do help sign like that, it will actually find something because it knows that you might spell it with an E at the end because that's what the actual name of that mathematical function is. You can also just do help. So it'll just it'll just give you these options to see these resources. Click and go to them. You can also do this one. I've actually never really used this one, but you can hit Doc 10 and it takes you directly to the MATLAB documentation for tangent stuff right there, and that's it. So the help key is very useful, especially useful when you're doing more advanced things and you're not really sure. You're like, what is the floor function? So you put in floor function. You're like, how do I use the floor function? So you help floor function, and it says, okay, the floor rounds towards minus infinity. Floor x rounds the elements of x to the nearest integer towards minus infinity. Oh, okay. So if I take the floor of the sine of x, if x is pi, for example, because we said that we got an answer for the sine of pi that was very close to 0, but it wasn't 0. So if I do this, I should get 0 because it's going to take that number that's very, very close to 0 and it's going to round it down towards negative infinity, which would be 0. And it does. And that's great. Because sometimes you don't want that thing to come out as a very tiny number. You want it to come out as 0. So you just floor it to 0. Call it good. Right? All right. So, page 68, bottom of the page, table 3.1, has a table of a bunch of math functions. You also have, the absolute value, which is ABS. So if you do the absolute value of negative 90, for example, it'll come out 90. You can also do the absolute value of a complex number, like the square root of -1. So if I do the square root of -1, which comes out as a complex number I, and I take the absolute value of that, it gives me 1, because the square root of -1 is I, but the absolute value of I is actually 1. So nth root is an interesting one. You can use this when you need to find like the 7th root of a number, right? So the nth root is just it's nth root, actually, nth root, like that. So you put in your number, say 45, and what root do you want to know of it? I want to know the cube root of 45. I hit enter, turns out to be 3.5569, and all of a sudden you're a genius, because figuring out cubed roots is really difficult. Sine. So the sine tells you the sine of a number. So if you want to know the sine of -4, for example, it tells you the sine is -1. If you want to know the sine of 4, it tells you the answer is 1. So -1 means it's negative, +1 means it's positive. But why would you want to know the sine of a number if you already know the number? Well, if the number is inside of your program tooling away, and your program is this long thing, and there's this variable in there that's kicking around and changing all the time, maybe because of calculations being done on it, and at some point during that program, all you need to know is whether it's positive or negative, then you can call this. You say you have some variable out there, you don't know what it is, and you do the sign of that variable, and it's running through your program, and it spits out all the signs of that particular array, because this array happens to be a huge array right now. X is a big array. So it's told me the signs of a bunch of them are negatives. So this was the array that we created to make that sine curve when we were graphing that sine curve. And a bunch of those numbers in that array are negatives, and then a bunch of them are positives. And maybe somewhere in the middle, one of them is 0. Let's see what happens if we do if we ask for the sine of 0. Yeah, it gives us 0. There we go. Doesn't have a sign. I don't know where that shows up in here, but it should show up in here somewhere. Right about here somewhere. Well, apparently they don't cover 0 on theirs, but if they did plot a point at 0, it would have showed up right there, but it didn't. Remainder we already did. Exponent. We talked about the exponent. That was that natural exponent we talked about. The log of x, the log base 10 of x. So if you remember something from like college algebra where you did logarithms, the natural log of a number, what it does is it asks if I raise, let's see, what does it do? it asks what what this function does is it says, what number do I need to raise e to get 8, right? So e, the number e is 2.78, something like this. This is e right here. Whoops, that's not e. Log e. No, that's not right. Yeah, that's what I got to do. The exp. So the exponent raised to the first power gives me 2.781, whatever it is. And if I take the log of that, it tells me the answer is 1. But if I put another number in there, like the log of 8, what it's asking for, where did I do that? Log of 8. It's asking what number do I have to raise 2.781, whatever, to get 8. And so when I hit return, it says, oh, you have to raise it to the second power to get 8. So if I write here 2.781 and I raise it to this power that it just gave me, which is called answer, so I'm going to just call it answer, I should get something close to 8. And it's 8.388 because 2.781 is not correct exactly. It's a little bit high apparently. But we also have a log 10, which makes a little bit more sense to people. So log 10, this one asks what do you have to raise 10 to get this number? So if I put 1,000 in here, what should the answer come out as? What's that? 3. You have to raise 10 to the third power to get to 1,000, right? So it's 10 times 10 is 100 times 10 is 1,000. So we should get 3, and lo and behold, we do. And of course, it's easy for powers of 10, but if you have something like log 10 of 43, that's not an easy thing to calculate. You know, it's something less than 2 and more than 1, but you don't have a clue what it is. It's somewhere between 1 and 2. Turns out to be 1.6335. Right? So that's a very useful function. Of course, your calculator has almost all of these functions. The only one that I can say your calculator probably doesn't have really is the sine function, but it's obvious what it is on your calculator because you're not writing a program, you're just calculating numbers, so it's just right in front of you. In this example that they do here, they're having us enter in a function and calculate some things to do with weather. Let's see what they're doing. They're calculating let's see. They've got, so they're entering in some temperatures and they're calculating out latent heat of vaporization, essentially. So latent heat of vaporization is calculated in something that they tell us here. I guess it's that first equation. Yeah. And so what all they've really done here in this section is they've started with an array of numbers. The array of numbers is these temperatures. Maybe we call this array temperature or something. Remember, when you're naming variables, it's a good idea to use something that makes sense. You know, if it's an array of temperatures, call it temp or temperatures or something like that. Whatever you want to call it, temperatures. No problem, whatever. And then you make that equal to an array of numbers, and they used -60, and they also used -40, and they also used, or -50 and -40, -50 and -40. So those are the numbers that they plugged in, and they did it all the way to 120. So instead of doing it this way, entering them all in, they probably did, and I didn't actually check how they entered it in. If we look on the code, I didn't really look, but I wouldn't want to type all these in all the way up to 120. I would actually want to go from -60 all the way up to 120 by tens, right? So I do a -60, and then I do a colon, and then a 10, and a colon to 120. Remember that trick that we used last time? And that's going to create this array of temperatures that goes from, if I open it up here, goes from -60 all the way up to 120, 19 entries, all in one row there. Very simple. And then they calculated, the first thing that they did is they actually converted these temperatures. So they convert these temperatures to Kelvin. Kelvin takes temperatures. So if you're not familiar with the Kelvin temperature scale, it's essentially a temperature scale that starts where 0 is actually the lowest temperature possible in the universe, and then goes from there. And our Fahrenheit scale is actually a German scale that's based on the lowest and highest temperature in a particular town in Germany. I think like Dresden or something like this. And that's not very scientific. So we don't like the Fahrenheit scale. And the Celsius scale is based on the temperature of freezing water and the temperature of boiling water. And if you're in biology or chemistry, then it makes sense because water is important in biology and chemistry. To an engineer, it's just another molecule, so it doesn't matter. So we go to the Kelvin scale and we do something a little more scientific. And converting to the Kelvin scale, they actually have that conversion in here. And it's just been, you end up doing make a new array, temperature, call it temperature subscript Kelvin or something, whatever you want to call it. And that's going to equal my array of temperatures that I made before. And I'm going to do some things to it. It turns out that you have to add some numbers to it and then multiply it by something. And so the number they have to add to it is 459.61. And you're not expected to know how to convert these things. I just want to show you what they're doing in that example, because this is all physics or math and science. It's not really part of the programming, except that it's good to know how to do the programming. And then you have to divide by 1.8, it turns out, to get the Kelvin. So once you do that, then you've converted all your temperatures to Kelvin, and they're in this new thing called temp Kelvin. Every one of those temperatures has been converted to Kelvin temperatures. I'm in the middle of, towards the end of the example 3.1 on page 71. And then the last thing that they did is they took this equation from page 69 and they solved it using some algebra for that delta H thing on the right side of the equation. And they don't really, I don't think they really showed how they solved it. They kind of showed the steps for solving it on page 70. But again, that's more math and science, and we're not really trying to teach you the math and science here. We're just trying to teach you the programming side. So if that makes sense to you, fine. If it doesn't and you want it to make sense, you can come and talk to me. But just realize you're not going to be asked to solve equations in this class. It's not something that we're going to expect of you. You'll learn that in your math and later science classes. But once they've solved that equation, then they create an equation for delta H, and they call it delta H, like this, and delta being that triangle in front of the H. And then they put in that equation here using temp Kelvin as the temperature, and other things in that equation they actually plug in numbers for that they already have. So the other things in that equation include this P with the superscript 0. They have an equation for that. It's a pressure, or a number for that rather. And then underneath that they have an R air, which they have a number for. And the T on the right side of the equation is the thing that we plug in our temperatures in Kelvin for. And then it calculates all of these things all at once, which gives us the answer for the what is it called? The something, I don't know what it's called. Something to do with weather. Humidity. Yeah. The relative humidity. So they're calculating relative humidity, which tells you a lot about whether or not a storm is going to happen, whether or not you're going to get rain or snow or something like that. So that's just kind of an overview of what they did in that example. And I don't like to do a lot of the examples because I don't want to waste a lot of time doing solving of equations and confusing people that maybe haven't, taken a physics class and understand everything in there. I realize that most of you probably wouldn't have any problem with it, but I just don't want to mess with that if we can avoid it. So we go on to the next section. So we're on page 72 with rounding functions, and introduce you to some rounding functions next. Oops, invalid expression. So we have already shown you one rounding function. That's the floor function. And that's in that chart on page 72, second to last one, the floor function. There's also a ceiling function, which is the last one that does the opposite thing of the floor. The floor function rounds everything down to the nearest integer. So integers being, the whole numbers, positive and negative and 0, right? The ceiling functions rounds everything up towards the higher positive integer. So if it's 0.0000000000001, it rounds it up to 1, right? Whereas the floor function would round 0.99999 down to 0. So those two things just do opposite, they kind of do the opposites of each other. But then there's always the round function, which is much more general. The round function actually has, let's see, yeah. So the round function actually has two different ways you can use it. So if we put round in here and put help in front of it, help space round, we can see that round can actually have two inputs. It doesn't just have to have a number input to it. You can put two inputs in. So what the two inputs do, the first input tells the computer what number you're rounding, and the second input tells the computer what to round it to. So what number to round it to. So if you want to round pi to the nearest 100, you put in pi, comma 2, right? And if you want to go the other way, so going down in size in the number, you put in positive numbers. But if you want to round to the nearest kilometer, and this is the number of the radius, the value of the radius of the Earth, want to round to the nearest kilometer, then you put in a -3 and it rounds this way. So rounding to bigger levels is a negative number, lower levels is a positive number. I know it's weird, but so let's try it out really quick. Let's round pi, and let's round it to the 10th. So what are we going to put in here? But if we're rounding pi to the 10th place, what number do we put in here? A 1, because a 1 means the first number after the decimal. Okay. Now, what if we want to round pi to the ones? What if we want to round pi to the ones place, the nearest ones? We would put put a 0. There you go. So that rounds it to the nearest 1, or the nearest number, integer, right? And if we want to round it to the nearest tens, we put -1, right? Round this to the 10th place, then it rounds it to 0, because the default for rounding is just like you learned in math class. The default for the round number is that if it's 0.5 or above, it rounds up. If it's 0.5 or below, it rounds down. And that's the same. So that works, if it's 5 or above in any place, actually, it rounds up. 5 and then if it's, 4.9999 or whatever below, it rounds down. Or 4 and below, it rounds down. So this one was 3, so it rounded down. All right. Another one is the fix, right? So the fix number is kind of interesting. It also has multiple numbers that you can enter into it. So we're going to fix this. We're going to fix pi again, and we're going to fix it. We're going to use the first number that we used. The first one was pi and 1. So I'm going to do fix pi comma 1 and see what happens. Oops. Apparently I did that wrong. Oh, no, it doesn't have 2 options. I thought it did. Fix. Okay. So here, let's actually do this one. Let's fix 9.8. So what does it do with 9.8? It fixes it to 9. It rounds it down. But if we fix -9.8, look what it does. It fixes to -9. So it didn't round it down. It rounded it up, because -9 is actually smaller in value, or more closer to the positive side, I guess is a better way to say it. So what this one does is it actually rounds towards 0 every time. So if it's a positive number, it rounds down. If it's a negative number, it rounds up. Okay. That's the fix. And then the floor and the ceiling we already talked about. All right. Now, discrete mathematics. You've probably done some discrete mathematics at some point in your life. Like when you did statistics, you probably learned some discrete mathematics where you did something like factorials, something like that. Or that's really the most common place that discrete mathematics is used besides basic kind of the very beginnings of division and multiplication. In the very beginnings of algebra, you learn things like factoring. So when you're factoring a number, you can talk about the prime factors, for example, of a number. That's discrete mathematics. Discrete mathematics means that all the numbers are integers and we're not messing with any decimals or fractions or anything else. And so that's what these functions, these next functions are all about on page 73. So you want to find the prime factors of a number, factor, put any number you want in here just at random. Find the prime factors of a number and it will find you the prime factors of that number. Turns out that I actually picked a winner right there. There's only 2 prime factors. It's kind of crazy. If you hit the prime factors of something that has something that's a bit smaller, 3 times 3, right? Here, if you take these 2 numbers, 601, and you multiply 75,931, then you get this number that I plugged in there, right? And of course, 3 times 3 is equal to 9. That one was obvious that it only has 2 prime factors. These 2 numbers multiplied together equal 9, and you cannot break these down into smaller integers at all. They're as small as they get. And that the reason I was surprised when I did this is because it's not very common for you to find a number that only has 2 prime factors. Even if it's an odd number, I just randomly picked numbers and I randomly picked an odd number. But if I randomly pick numbers again, they're the prime factors. That's much more common. They have a much larger amount of prime factors. Here we have, you usually get a lot of 2s for even numbers, or at least one. Yeah, you always get at least 1 for even numbers. And then, having a 3 in there every once in a while, and then this huge prime number here, it's kind of interesting to do that. But if you need to know the factors, the prime factors of a number, that can be useful, very useful. I don't know if there's many calculators that can do that. Probably there are some these days, but that's not necessarily an easy program to write. We could write it actually. It's not terribly difficult for smaller numbers, but once it gets to bigger numbers, it starts to be a little bit, you have to be clever to get it right. Then you have the greatest common denominator function, GCD, right there. It has 2 inputs. The first number that you input is, whatever number. And then the second number, you're trying to find the greatest common denominator between the 2, right? So do they have a greatest common denominator? It turns out they do. These are 7. For these 2, it's 7. And that was obvious. I picked those numbers that way on purpose. If you do the greatest common denominator of, let's just do some odd number and see if there is a greatest common denominator between these. The only one is 1. So obviously 7 is not a factor of these 2. And you can also do 2 large numbers, see if they have a greatest common denominator. They do not. Then we have also lowest common multiple, LCM. These are things you probably remember from early math classes. Turns out that 456 is a multiple of 8, but 8 is not a multiple of 456. So we could do 80 also. So the lowest common multiple between those two is 4,560. So you have to multiply 456 by 10 to get the lowest common multiple. Oh, so that's great. Okay. Then we have this RATS function. So RATS is the function we kind of saw it earlier, where you can express something as a rational function, a rational number rather. A rational number is a number that is expressible by putting one number divided by another number, right? So just about all real numbers are rational numbers. Well, no, sorry, not all real numbers are rational numbers. Many real numbers are rational numbers. Many of the numbers that we deal with on an everyday basis are rational numbers. For example, 1/8 is a rational number. If I put 1.125, it knows that the answer that 0.125 is 1/8, right? But if I put in pi into here, pi is not a rational number, but according to MATLAB, it is, because MATLAB cannot actually store irrational numbers. An irrational number is a number that has a never-ending decimal, right? And so it can't store that. A computer can't store something with a never-ending decimal. We don't even know what pi is out to infinity number of decimal places, right? We can't possibly know it. And so the idea of trying to rationalize pi is too much for MATLAB. It just rationalizes the number it has and calls it good. So irrational numbers, you can't really make this function fail in MATLAB, because MATLAB can't store an irrational number. So any decimal number you want to put in here, it could be 8.56238 or something like this, and it can do that, no problem. So just creates a fraction out of it. All right. Now, anybody remember what a factorial is? Yeah, so you start off with a number like 10, right? And then you multiply it by 9 and 8 and 7 and 6, 5 and 4 and 3 and 2 and 1, and that's the factorial of 10. Right? And why would we use such a thing? Well, factorials are very useful in calculating the number of possibilities of something. So they're very good for doing statistics. They're very good for doing for calculating the odds in a game, right? The odds of winning, like the odds of getting a royal straight, right? A royal flush, not a royal straight, a royal flush. There's only 4 possible ways to do that with a 5-card hand in poker, right? You can do it in clubs, you can do it in spades, you can do it in hearts, you can do it in diamonds. And that's it, only 4 ways. But there are more than 200 million different ways that you combine the cards in a deck of cards. So the chance of getting one of those 4 is 4 out of 250 million. But how did we get that 250 million or that 200 million? Well, that 200 million was counted up using a formula using factorials, because you always have to think, well, I take 1 card out of the deck, so I have a 1 in 52 chance of pulling a king out of the deck, a king of diamonds or something. But the next card I pull out, I have a 1 in 51 chance of pulling the queen of hearts. And the next card, I have a 1 in 50 chance. And the next card, I have a 1 in 49 chance of pulling out that 1 card that I need for that. And so it ends up being 1 in 200 million something, right? And yet, how many movies have you watched where it's playing poker and the person wins with that hand? You have to watch 200 million hands for that to happen. And there's no way. I mean, almost nobody who plays poker professionally has ever seen that happen. Almost nobody who plays poker at all has ever seen that happen. I've never seen it happen. It just almost never happens, because nobody has enough time in their life to play 200 million hands of poker. You don't have enough seconds. You're not going to live that long. So, so the likelihood of it happening in every movie, every story about poker is just ridiculous. But it's, makes a great dramatic ending to a movie. So most people end with like, a full house, something like that, something much more common, much easier to do. Kings over twos or something. Anyway, so that's what that is used for. That's what factorials are used for. And you can do factorials of a number. You can do the factorial of 41, for example, and you get a huge number. Factorials get very large very quickly. You do the factorial, start off with the factorial of 1, of course, is just 1 times 1. And then you start off with then you go to the factorial of 2, and you get 2 times 1. And then the factorial of 3, and that's 3 times 2 times 1, which is 6. And then the factorial of 4. And these seem pretty, simple. Factorial 4, 24. But then all of a sudden, things start to get a little bit out of hand in a quick hurry. Right? I mean, you're not even up to 10 yet, and we're already up to halfway to 10,000, right? And then we're at 40,000. And of course, that jumps up to 362,000. And then all of a sudden, the factorial of 10 is no laughing matter. So if anybody comes up to you one day and says, I'm going to give you a penny today, then I'm going to give you 2 tomorrow, then I'm going to give you 3 the next day, I'm going to do that for 2 months. What do you say? Yes, please. Right? Because you'll be a millionaire in 2 months. Well, you'll have a lot of money in 2 months. I don't know exactly how much money that is, but it's probably $1 million or more, or a lot more. Let's see what it is. To do that math the other way is a little bit more complicated. But anyway, here we go. Here's another thing. This next function, n choose k, yeah. And choose k. This is actually shorthand in statistics for calculating the total number of possible combinations of doing something. So this will tell you the total number of ways that you can arrange a 5-card deck, for example. You're going to have 52 cards to choose from, and you're going to choose 5 cards from the deck. So let's see how many that is. It should be a big number. 200, no, it's 2 million, not 200 million, 2,598,000. So even if you played poker every day of your life, 5 times a day, you're never going to play 2 million hands. It's not 200 million hands, but it's 2 million hands, but it's still never going to happen. Because that's a lot of days. I think the average human only lives, so if you did 100 years times 300 days a year, that's 300,000 days that you live. You're not even living a quarter of that. Not even you're hardly living a tenth of it, barely. So that's a lot. But anyway. All right. So primes is find all the prime numbers less than x. So primes. So all the prime numbers less than 10 are 2, 3, 5, and 7, because all these numbers can only be divided by themselves in 1 to get a whole number, right? If you do 100, you get a few more. If you do 1,000, get a few more. And the higher you go, the fewer you find, the fewer more that you find. We found for 100, for 1,000. Let's see, which one did we do for? Let's do this again. For 100, we found 25 of them, right? For 1,000, we found 168 of them. For 10,000, we find 1,200 of them, right? So we're not quite like, it's not like you go 10 times bigger in number, you find 10 times as many. You don't. It increases slower and slower the higher you go up, because more and more numbers tend to be multiples of other numbers at that point. So this is actually a science that it's kind of its own. It's not really a science. It's more of a mathematical exploration. But there are people out there that spend all their lives trying to find the next prime number. It's kind of weird, but they do that. There is a reason for it. One of the reasons for finding prime numbers is that prime numbers are one of the keys to making things secure with a computer, with a mathematical function. If you can create an algorithm that's kind of designed around a prime number, especially a really, really high prime number, it makes it a very difficult code to crack. And, computer codes are not about, really crazy programming, lots and lots of lines of code. They're actually more about things like this, like prime numbers. So you can write code that takes up 8 kilobytes or something like this, and that would be absolutely unbreakable because it doesn't take much. It takes hardly any memory to create the code. It really just takes mathematics, and the mathematics is the thing that makes it difficult. So anyway, the problem with security like that is that when things are that secure, it's hard to use them. So it's kind of, you get a return, diminishing returns for security. And then the last one is the is prime. So the is prime function, whoops, that's not what I'm trying to do. This is a algorithm that tests the number to see if it is a prime number. So if I ask, is the number 45 is prime, right? It says no, 0, right? If I ask, is the number 7 prime, whoops. If I ask, is prime 7, then of course it does. Is prime 17? Yes, right? Is prime 29? Yes, and so on. I don't think it'll do anything for negative numbers because negative numbers can't be prime by definition. All right. If you try to take a factorial of a number that's too big, you'll get in trouble because it can only do so much. It just becomes a number too big for the computer to mess with. It just gives you infinity. All right, so that is those are all of the functions for rounding functions, discrete mathematics, and so on. We also have the whole mess of trigonometric functions, sine, cosine, tangent, page 76, sine, cosine, tangent, hyperbolic, sine, hyperbolic, tangent, the arc tangent and the arc sine and the arc cosine are all there as well. There are so many different there are so many different trigonometric functions. You don't need to know what they're for, what they're used for. You just need to know that MATLAB can deal with them. Two of these that are quite useful. There's a few of these that are quite useful. I mentioned before that the sine, the cosine, and the tangent expect to get an angle in them that is in radians. If you're not used to that, you can actually use the sine d. Sine d will take the sine of a number in degrees, which is of course what we're used to. So the sine d of 90 degrees, for example, should be 1, and it is. And the sine d of 180 should be 0, and it is if you use sine d, right? Because that accepts the thing in degrees. So if you use any of the trigonometric functions with a d on the end, then it works for degrees. And you can also convert from radians to degrees. So if I do rad to deg, rad to degrees right there, not with a 2, but with the number 2, rad 2 dig, there we go. And you put in a radian measure, so I put in like pi, then it knows that pi is equal to 180 degrees and it returns 180 degrees. And you can do degree to rad, radian. You do the same thing there and plug in 270 degrees, which should end up being, well, this answer is in decimals, but this is actually 3/2 pi. So it's 3.14 times 1.5, which is 4.7124. It doesn't give it in terms of pi. It gives it in terms of how many radians that is. So those functions are all available to you and just really kind of straightforward to use. And that takes us to the end of kind of the mathematical functions, kind of those basic mathematical functions, and to section 3.5. Does anybody have any questions about any of those functions Anybody have trouble plugging them in? Anybody have any questions about other mathematical functions that MATLAB might have that we didn't mention here that you might be interested in? Yes, it can. So the combinations is this one here. That's the one we saw. That's the n choose k. There are several other versions of that, and if you type in help, so that's the combinations one. Permutations, so that you have to choose them in a row. And let's actually do help. Let's do help discrete. So if you go to the discrete functions page, so let's see, discrete eyes. No, that's not what I want. I'm going to do help and choose K and see if it takes me to where I want to go. Oh, here it is, perms. So it's actually, you can do random permutation, you can do permute, and you can also do perms. So all the possible permutations function is perms. So yes, you can do that. And this is actually, this one, I'm misleading you. Perms is actually for the permutations of a vector or a matrix. And so you're not gonna use it the same way you would use n choose k. You can do that with this function, but you use a matrix to do it. I'm gonna guess that random perm, yeah. So the random permutation of the integers from 1 to n. So if you have, 52 cards and you do random, see, what is it called? Rand perm, and you have 52 cards, the total number of random permutations, they actually, let's see, what are they showing us here? No, this is not right. That's not the right one either. So sometimes you just kind of got to look and see what they do, first of all. Random permutations. See, rand perm returns vector containing random permutations. Oh, here we go. So rand perm with two, what you call two numbers. So if you want to do the random permutation of 52 cards with choosing 5 card hands, you do 52 comma 5, and then it tells you they're doing, that's not what they're doing either. Five refer to the K permutation, one land sampling without placement. Repeated value 6 for 2 or sampling with placement. I think you'd actually have to multiply all these numbers together to get that. K unique values randomly from 1 to n. Explained by 425. K unique, the vector of K unique values. K permutation with replacement. Sometimes if you do sampling with replacement, you can do Randy. You can actually, so there's another one here. There's several different ways to do that apparently, but you can also, the other thing that you can do is you can calculate, you can use n choose k and then divide by 52 or 52 minus 5 factorial, right? Whatever the formula is for permutations. So yes, you can do it, but it's not as necessarily easy as doing the combinations one. And probably there is a function that we could make a function. It wouldn't be hard because the difference between the combinations and permutations is just a thing it's just another, it's like a 5 factorial in the denominator or something like that, right? Whatever it is. So it wouldn't be that big a stretch to create that function. But anyway. Yes, did you have a question or are you just scratching your head? Anybody else have a question before we move on? All right, that was a good question because I've never really thought about it, if we could do it. I've actually never used MATLAB to figure out the odds for something like that. So, let's see, data analysis functions. So now we're going to go into a different type of functions. Whenever you're dealing with large amounts of data, MATLAB has some great functions to help you to find things really quickly. And when you're trying to analyze your data, it's really important to know, for example, what's your biggest number in your data set? What's your smallest number? What's your average number? What is your, I mean, all these statistical things that you need to know about your information in these big data sets. It can be at a huge matrix or a list of numbers or whatever else. And we have these functions. So you can find the maximum and the minimum, and it's just max and min. For example, if I do max of the answer, which is this array right up above me, 35, 9, 6, 25, 24, 7. So I find the max of answer, it will return 47 because that's the biggest number in there. And you do the min of that, and of course, return, whoops. That's not what the minimum of answer. What is answer? Oh, answer actually only is 47. Answer is not that whole array. Never mind. It's actually, if I do the minimum of B, so B is this one that's 2, 3, 4. Answer only has one thing and it's only this last number. So if I do the minimum of B, that actually has 3 things in it, it gives me 2 because B has 2, 3, and 4 in it. Oh yeah. You can also if you do this for a matrix, you get a strange thing back. So let's make a matrix. They do this. They put together this matrix at the bottom of page 79. X equals, we're going to put in 1, 5, 3. So 1, 5, 3. And then on the next row, we're going to put in 2, 4, 6, 2, 4, 6. All right, so we get this matrix here. And if we do the max of X, it actually tells us the maximum in each column. And it returns it as a matrix of 3 numbers, 2, 5, and 6. And then if we do the minimum, same thing, then it shows us that, the minimum in each column. So minimum and maximum, when you ask it of a matrix, something that has multiple rows, we'll do it column by column by column. And that happens with a lot of matrix functions. A lot of functions that are designed to act on a matrix will do it column by column by column. So you have to be aware of that. And then you can actually set these values into another matrix, into another set of variables. So if I do, let's see, they're doing A comma B equals max of X. Right here. Then it's going to do now it's actually taking the max number and put it in A, so 2, 5, and 6, and then it's actually told us what element it is. See, so the first element is in the first row of column 1. The second element is in the second row of column 1. So 2 is the max for column 1, and it's in the second row. 5 is the max for column 2, and it's in the first row. 6 is the max for column 3, and it's in the second row. So they've given us, it actually extracts that information as well. Excuse me. Oh, and you can also do it for, so here's an operator. If I take X and I put a little single quote after it like this, it actually changes the rows and columns of X. So right now X has 2 rows and 3 columns. Now X has 3 rows and 2 columns, and all the numbers that were in rows are now in columns. So the first row, 143, no, sorry, the first row, 153, is now the first column, 153, right? And then the second row is now the second column, 246, right? And so this is what we call the transpose of a matrix. When you take all the rows, the first row, and turn it into a first column, second row, turn it into a second column, you switch everything from rows to columns in a matrix, it becomes the transpose of the matrix. So if you want to know what the, so if we do this, if we change this back, we do X, so that's extra. So X is, we didn't change X here. X is still equal to this thing. But if you want to change X, you would do X equals X prime, and that would change it. In fact, so let me show you. This is what X is equal to right now. If I do X prime, it shows me this, but it doesn't make X equal to that. X is still equal to this. But if I do X equals X prime, then it changes X to this new array that has 3 rows, 2 columns. So I'm going to change it back by doing X equals X prime again. We call that a prime. And then I'm going to take this and I'm going to say, I want to know the max in each row. Then I do the max of X prime. So it changes, it essentially is now going to look at the rows instead of the columns. And so I want to find the max of X prime, return that, and it finds the maximum in row 1 is 5, the maximum in row 2 is 6. And they can even find out what element of each row they're in by doing this thing right here. Nope, by doing this thing right here and doing a prime right there, and it'll tell me the element of A, that it's, you know, the maximum in row 1 is 5 and it's the second element. The maximum in row 2 is 6 and it's the third element in row 2. So you can do that. Okay, so that's the max and the min and all the accompanying things. The mean and the median. Does anybody remember what the difference between the mean and the median is? Yeah. So the mean is what we call the arithmetic average, where we add all the numbers together and then we divide by how many numbers we have, right? And the median is if you line all those numbers up from the smallest to the biggest one and find the one in the middle. And if there's 2 numbers that share the middle spot, then you take the mean of those 2 numbers, and that's the median. So if we have, let's put together some numbers here for our mean and our median. Let's see, what do they use? They're going to use this big old, I don't know what they're using. What are they using? They're not using anything. Let's just create a bunch of numbers. Let's create an array of numbers, shall we? Let's call it array. Let's call it grades. Let's give everybody some grades. So my grades array is going to equal this array of numbers. That's going to go from 0 to 100, right? So I'm going to have 0, I'm going to have 45, I'm going to have 89, I'm going to have 36, I'm going to have 56, I'm going to have 89 again, I'm going to have 97, I'm going to have 98, I'm going to have 99, I'm going to have 100, I'm going to have 25, I'm going to have 58, I'm going to have 54, 97 again, and a 63 and a 2. I've got a really wide arrangement of grades, right? You can put whatever numbers you want to put in, it doesn't matter. I have some zeros in here that shouldn't be there. I'm going to put a 0 right there. But any array of numbers, it doesn't matter what they are. I just decided to use numbers between 1 and 100. And in fact, well, here's this array. I'm putting this array together. So it makes this array called grades over here. Now I'm going to make an array of grades called random grades, rand grades like this. And I'm going to create another array using a function that I don't know if I've told you yet or not. It's called the random function. So if I actually go, I'm going to go here to help random, so you can remember to do that. If you don't know how to use it, help rand right here. So rand creates an array of numbers that are random numbers between 0 and 1. And you can actually tell it how big of an array to make. So, oh, and you can actually use rand integers, so randy as well. But if I want to have a random array of numbers that has 1 row and 5 columns, I do rand 1 5, right? And if I want to do it from 0 to 100, I can do that as well. So I'm going to do that right now. I'm going to call it randy. That's my random integer array. And it's going to be 1 row by 27 columns or something like that. Run 1 comma 27, right? Oops. Nope, that's 27 columns. That's not right. Where did it go? I don't like that one. Randy is not what I want to do. I want to do rand. So I'm going to do random number of arrays from, and I want to do random numbers. I want to do 27 of these. Let's see if it does it for me. So this actually did a 27 by 27. So I want to do it rand 1 row, 27 columns. There we go. So random, making a random number array 1 by 27. So I'm going to call this my rand grades. Random grades, like that. It's going to equal rand 127. And notice what I did there. I did some things in rapid succession. If that confused the heck out of you, I apologize. But I just plugged in a function and tried some numbers in it to see what it did. That's totally a great way to learn how to program. Just try something out and see what it does, and then play with it and see what it does. Sometimes it's faster than reading the instructions and trying to figure them out. So, and that's usually the way I do it. I just kind of try it out and see if I remember how to do it. And if I don't, then I try to fix it. And I discovered that if I put rand 1 comma 27, it made a random array of numbers between 0 and 1 that is 27, has 27 things in it, right? 1 row, 27 columns. But I don't want this to be decimals. I want this to be like percentages. So I'm going to multiply this by 100. I'm going to do 100 times this array, and that's going to be my new array of random grades. So there's another way to make a random array of numbers between 1 and 100. And I can pick however many I want by just setting the number in the rand function. So if I open my rand grades array, you can see that I have all these percentages between 0 and 100 that are random. I could even, if I wanted to get rid of those decimals, I could even say, let's round all those numbers up, or round them all down, or just round them up or down, depending on how they should be, right? So I could do a round out here, or a ceiling, or a floor, or something like that. I'm just going to do a round function on the outside. Now I've got nested functions, multiple nested functions, and I hit return again, and I look at my random grade array, and it's all of a sudden doesn't have any decimals in it. Much cleaner, right? Now, getting back to what we were doing, let's take the average. If I want to do the average of these things, then I do the mean. I do the mean of random grades, rand underscore grades. And this will return the average grade in that class, 48.7778. That's not a very good grade, but bell curve. Or I could do the median. So the median of these grades will line all these grades up in order from smallest to largest, and it'll look for the one in the middle. Oops, median, not medium. Median, there we go. Turns out the median grade is 50. Well, that makes sense, doesn't it? Why does that make sense? Well, no, this isn't an actual set of grades from actual students, right? This is actually just a set of random numbers that I chose. But both my mean and my median are really close to 50. And that makes sense because I took a random number between 0 and 1 to start with. And if you pick enough random numbers between 0 and 1, your average is going to be 0.5. And if you multiply that number by 100, of course, you're going to get 50. It's like flipping a coin, essentially, right? This is actually very much like flipping the coin. Now, how does MATLAB get a random number? Can you create a function that makes a random number? Can anybody think of a way? If you were going to just pick a random number, how would you do it? Well, you would just say a number. But the problem with that is that inside our mind, we have created numbers that we like, numbers that we don't like, responses to questions, all kinds of things. We're very likely to pick a number that's close to our age, for example. If we're asked to pick a number between 0 and 50. In this room, if we asked people to pick a number between 0 and 50, most likely you'd pick a number fairly close to your age. And if you averaged it out, if they asked you to do that 100 times, it'd probably average out to be about your age. And that's not very random. That's because it's your age, right? And if you ask somebody to pick a random color, they're going to most likely pick a color that they like, or something that they associate with their life every day, or something they've seen recently a lot of, right? So things are not very random. You ever wonder, there's a hypnotist coming on campus. You ever wonder how hypnotists do their thing? They do their thing like this. This is one of the tools that they use. It's not the only one. The biggest tool that they use is that they just lie. They actually have tricks and things that they've done before the show, and they have certain ways of asking questions to people, and they have observers and assistants in the audience and all of these things. And believe it or not, that is happening at every one of these things. There's no such thing as telepathy or anything like that. It is absolutely false. But these people also know that there's no such thing as random when it comes to the human. So they can look at a person and see that they're wearing a profusion of red and know that that's going to affect their answers. And they can look at somebody and say, this person is obviously, from this town because they're wearing something that says Nebraska on it. They're a Cornhusker fan or something. So obviously from Nebraska, and that's going to probably color it red, their answer, right? In some way, they're going to be guided towards something. They look at race, they look at age, they look at clothing style, they look at everything, and they know that actually can have a high probability of pointing you in a certain direction for your answers, right? But how do you do a random number on a computer? Well, the interesting thing is that a computer has a clock in it, and that clock does not keep time the way we keep time. It keeps time in a very different way. And then if you go and query the clock, if you ask the clock what time it is, it gives you a number that includes date, and it includes the date and the time of day, but it's not like, well, this is the 6th of January and it's 12 o'clock. It's actually just this long string of numbers that is not really related to that until you plug it into an algorithm. You have to plug that long string of numbers into a function that then calculates the date. It doesn't just extract it and say, well, these numbers are the date and this is the time. It's not that. You actually have to calculate it. And so that number is just about as random as anything can get on a computer. And then they take that random number off of the clock and they put it through an algorithm that actually creates more randomness. That algorithm actually changes depending on different things going on in the computer. So the computer is constantly monitoring the temperature of the CPU. So it might take the temperature of the CPU at that moment and plug it into that algorithm to give it a random element and to change things a little bit. It might also take the last place you clicked on the screen. You might take those coordinates and plug them into the algorithm and include that as a random element. And so it's a lot more random than we can choose, right? So the random numbers coming off a computer are always going to end up giving you this kind of probability that you would expect from random numbers. If we had a random grades file that was had a million different grades in it, this would come out to 50 and 50 every time, because it's just flipping a coin, essentially. It would come out right in the middle every time, or very, very, very close. Anyway, so MATLAB can do that. It can do random numbers and it can do them quite well. So that's your mean and your median, and it can do the entire matrix, and it can do all kinds of things. You can even choose a single column out of it and do it, and we'll learn more about that later. But the last one that they do is mode. So does anybody remember what the mode is of a? Yeah, so it's like the most popular grade, Mode meaning like a la mode, which means in the style. It's the most fashionable thing. So if I do the mode, it turns out the mode of random grades is -96. Why did it put a negative number in there? Random grades doesn't have any negative numbers, does it? Mode, oh, that's a problem because I did random minus grades, not random grades. This should be an underscore. That's a very common coding error is when you have an underscore in the name of something and then you put a minus instead of the underscore because you forgot to hit the shift key. And then those two things happen to be variables also. Then you get a very common coding error. But it turns out that the most common one is 24. Don't know how many times it exists, but I think you can actually return how many times it comes up as well with the mode. I don't remember how to do that. I think it might be something like this. I think you can set it equal to two things. There we go. A comma B equals mode grades maybe. Yeah. So 24 is the most common one and it happens twice. And it happens right there at 3 and 4. How about that? It's not even like spread out. It's just right in a row. Apparently the clock didn't change much between those two. And nothing else did either. All right, so those are your data things. What do they call them? Data analysis functions so far. It is now 3:30, no 2:30. We have about an hour left. So let's take a little bit of a break, 5 minutes, get up, walk around, get a drink if you need to, I need to. And we'll come back here in about 40, about 2:40, 4 minutes or so. right. Let me do that really quick here while we're thinking about it. Calendar. Chapter 2. Today is Wednesday, right? Oh, yeah, I set the time on it at 10 a.m. is the reason, right? Okay, so let me fix it. I'm just going to put it to the next day, and then you should be able to do it. Sound good? All right. Yeah, if you ever like forget to turn something in, just tell me, and I can move the due date so that you can turn it in. But I want you to try and get things done and not leave them. I don't want to be doing 4 or 5 assignments at the end of the semester, but want to try to keep up with them. But if you just miss it by a day or a couple of days even, I'm fine with that. So not a big deal. This one right here, want me to move it to here? Oh, this one's not due until tonight. No, it's 11 p.m. So yeah. Do you need more than today to do it? Like you can finish it tonight by 11? Okay. Yeah, and I can move it to tomorrow if anybody needs that. I don't mind doing that. I just don't want to have people doing 5 assignments at the end of the year because then you won't have time for your project. And really, I try to design my classes, most of my classes, so that the hard stuff is kind of in the middle of the year. And then at the end of the year, when all your projects are coming due and all your other classes, you're not having to worry about physics or engineering or mathematics or something, because those classes are hard enough without having to jam a bunch of crap at the end of the year. I try to make mine easier towards the end of the year so you can do other classes as well and not be super worried.
Just a question, so I'm not like maybe doing something wrong. The assignments, as you said, like it's like 1 to 7 and everything. Are those the problems at the end, the 2.1?
Yes. Yes. So the problems in chapter 2, for example, begin on page 55. And so 2.1 is problem 1 in chapter 2 and 2.2. So you'll do all of problems 1 through 7 in one script in MATLAB, one file in MATLAB. Save all that code to one file and then upload it. And then do the next ones on the next file and upload another file. Yeah. And the reason that I did that is I tried to group them in ways so that you wouldn't have to use multiple files to upload the code, and also so that I wouldn't have to like sort through a ton of code per question. So it makes it easier for you and easier for me. As we get on further through the class, you're going to have to upload maybe 2 or 3 files per problem, because you're going to be creating a function that you have to save in one file, and you have to have a bunch of data that you save in another file, and then the actual code that you write is in another file. And so that will have a different format, but we'll see that when we get to it. Okay. Any other questions before we get started again? Chapter 3. All right. Well, let's go to, let's see. How do I bring my sharing window to the front? Resume share. MATLAB, that's what I want. There we go. All right, so Logan, can you see my screen again there? Are you still with us there, McCook?
Yeah, I'm here.
You see my screen?
Yep.
Okay, good. All right, so back to chapter 3. We're in sums and products. Let's see how much we have left here. Variance, standard deviation, random numbers, which we already learned a little bit about. Complex numbers, which we would mostly skip. Computation limitations, and that's the end of the chapter there. So we're doing good. We'll finish up. Good. All right. So sums and products. I'm going to clear my screen here. Yes, that's what I meant. I'm going to clear my variables out too, just to have a nice fresh start. So you can add up the numbers in a vector. You have your vector X, whatever it is. You can multiply the elements in a vector. You can do a cumulative sum of vectors and a cumulative product. These are 4 different functions, all on page 83 in this section here. And the sum of X will add up, I think, every single, let's see, no, it'll add up if the vector is just a row vector. This is what you get. So let's actually make our vector. They're doing X equals 1, 5, 3, right? X equals 1, 5, 3. So if you just have that vector and you do the sum of X, it just adds 1 plus 5 plus 3 and gives you 9. However, if you have a matrix that looks more like this, 2, 4, 6, 6, right? And you do the sum of this X, right? It adds by column again, right? So we've seen this before where we got the average of the column, where we got the, what was the other thing that we did? We got the max of each column. So when you start using these functions on a matrix that has rows and columns, it has a tendency to do it by column. So you're going to get the sum of each column, and it's going to create a row vector of each one of those sums. The same thing works for the product. If you do the product of X when it's a matrix, prod, it's not product, it's prod. Do the prod of X, which is the product of X, it gives you the product of 1 times 2, the product of 5 times 4, the product of 3 times 6 for each column, right? And you just have to realize that that's the case. However, if I do the product of the answer here, the answer, which is just this row vector, doesn't have any, it has 3 columns, but it only has 1 row. So if I do the product of answer, it actually multiplies 2 times 20 times 18. So it just goes straight across the row, right? So that's kind of an inconsistency with MATLAB. If it only has a single row, it just multiplies across the row, adds across the row, takes the average across the row, everything else across the row. But if it has multiple rows, then it does it by column and returns a row of averages or products or means or whatever you're doing there. So that's just something you have to remember about MATLAB. It has that little quirkiness to it. I actually don't know what happens if we do, like, let's do a vector y, and let's say y equals, let's do a column of numbers, 3 and then 4 and then 5, like that. And let's do the sum of y and see what happens, because I don't know what happens. I don't think I've ever thought about that one. Sum of y, what happened? Oh, there we go, sum of y. So if it's a single column, it actually just goes straight down the column. So it works either way. If it's a single row or a single column, it just goes straight across. But if it's multidimensional, if it has multiple columns, multiple rows, then it goes down each column by default. And of course, if you want to go down each row, you can, just like before. You can do the product of each row by doing the transpose of X. So then it gives each row the product of each row of X, which would be 1 times 5 times 3 and then 2 times 4 times 6, right? It gives you 2 answers back. So that is, you can do that as well. Then the cumulative sum of X. This is a new one. The cumulative sum of X. What does this do? So it's returning now a vector that is the same size as the original vector X. The original vector X is this one here, 1, 5, 3, 2, 4, 6, right? But it's giving us something slightly different, right? What is it doing? Anybody see what it's doing? I'll open X for you. So what's it doing? What's that? Sorry.
Rewrites the values of the first row and then writes the answers in the second row.
Okay, so it's taking, so it looks like it's it looks like it's just copied the first row in there.
Copy the first row.
And then it's added the first row to the second row in each column and put the answer in there, it looks like maybe.
Every column is like added and then the answers are in the second column.
Yeah, yeah. So what it's really done is it's added the first row to nothing, to 0, right? And then put the answer in there. And then it's added the second row to the row before it and put the answer in there. And if we had a third row, let's put a third row of ones in here and see what would happen. Right? So then it takes this one plus this one plus this one and puts it in there, right? So the first row is the first row plus 0. The second row is the first row plus the second row. The third row is the first row plus the second row plus 0 plus the third row, right? And that's how it does it. That's the cumulative sum. Does that make sense? The only one that's a little confusing is the first one, because the first one, it's essentially adding the previous row to the first row and putting the answer there. But there is no previous row, so it just takes 0 and adds it to the first row and puts the answer there. And then it puts the first row and the second row added together in the second row. And then the second row and the third row added together in the third row, and so on for each column. Make sense? So again, there are many examples where this could be useful, right? This can be useful in many kinds of programs where you have iterative summations or iterative products. And of course, that happens all the time. There's a program like this that does like total values for the total. Let's take basketball. We got 2 basketball players in here, right? There's a program out there that tracks number of fouls in a game, right? Or the number of such and such in a game, or whatever it's tracking, right? And it takes that previous number and adds the next number to it. And it's a very simple thing to do, but that's what it does, right? And it can do that for however many players, and you can do it for 1 million players if you're doing this in MATLAB. I've often considered actually creating a program for tracking data in volleyball automatically. I thought about doing this, more than a decade ago, and now people have actually done it. I never actually got around to doing it. But the reason for that is because volleyball moves much more quickly than most sports. The average play in volleyball takes 3 seconds. Boom, done, right? And that's from serve to kill. The average volleyball play takes 3 seconds. At the professional level, it's more like 2 seconds. So it's a very fast moving game. And in those 2 seconds or 3 seconds, you can have as many as 15 to 20 different statistics on as many as 12 different players. And you can even have more than that if it's a crazy play. You can have up to 20, 30 different statistics. And these statistics are all valuable for determining what you're going to do in the next play, believe it or not. In volleyball, just like any sport, there's your head coach, and then you have your assistant head coach, and then you have like 10 other coaches that all they do is statistics. And at higher levels, at like Division I volleyball levels and professional levels. And all these 10 other coaches are feeding statistics to the 2 head coaches constantly and telling them the performance levels of different players in different areas. And then those coaches are deciding who's going to come out and who's going to come in for them at that point, right? To make sure that you have the maximum chance of scoring points. And that happens at every level of sports now. That's why these, coaches have these clipboards, and these clipboards are not clipboards anymore. They're computers, and they're tracking all these statistics all the time. They're looking down at a screen, it's tracking all these statistics. And then, they've got earpieces in and all these things. They're just being fed information constantly. And so that's what these computer programs can do. Anyway, so let's see. So here they're going to do an example of creating series of numbers or sequences of numbers, right? So oh, sorry, they don't show this. I don't have my book on the screen. So this sequence is 1/1 plus 1/2 plus 1/3. So the denominator in this series of numbers is always increasing by 1. This turns out to be a really important thing when you're doing things like calculus. Calculus is this kind of thing where you have this iterative number being generated and it's changing by some amount in some way every step. It's exactly what calculus does. And so we can create that pretty easily. And this is how we're going to create it. We're going to define a variable k. We're going to say k equals the number 1 to the number 5. And so that's just, that builds an array of numbers from 1 to 5. Right? And then I'm going to define a sequence of numbers. So this is a new array of numbers. And the sequence of numbers are going to be defined as 1 divided by k. But when we do 1 divided by k, we get this error. The matrix dimensions must agree. So we can do this two different ways. We can either create an array of numbers, an array of ones, and there's actually a way to do that. I can do an array of ones like this, 1s, 5. It creates an array of numbers, but it gives me this problem that array is way too big. It has rows and columns, and so I have to do this one. Rows, I want 1 column and 5 rows, so I'm going to do 1 comma 5 like this. So I can do that, and then I can do my thing here, where a sequence equals answer divided by k, and that gives me this. Let's see. Nope, it doesn't. What did that do for me?
You go all the way up, Professor, kind of like, and then you write it down, like you started, from K.
Where's k? So k is here.
Yeah, I think the line to put is just a little bit up.
Oh, I think I know what it did. I think I actually know what it did. So k is correct. But I think I know what it just did here. It actually did these things one by one and only gave me the last answer. So it gave me, actually, I don't know what it did. That's weird. But anyway, the other way to do it, which is actually the proper way to do it, I was trying to illustrate something there, but I apparently didn't illustrate it because I did either made a mistake or there's something weird in MATLAB that I'm not aware of, which is entirely possible. But the proper way to divide a number by an array of numbers is to do the dot divide, which we talked about earlier. Oops, dot divide. Because that says that we're going to divide every number, we're going to divide 1 by every number in this array, 1 by 1, element by element. So if I do 1 dot divide by k, then it does 1 divided by 1 and puts it in an array. And then it does 1 divided by 2, which is the next part of k. And then it does it all the way through all of k. So if I call this my sequence, it will work properly. So then you have 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4, 1 divided by 5. And you could even put it in, you could even make this a rational number. You could put this into a rational number using the RATS function that we learned earlier today. And then you get 1, 1/2, 1/3, 1/4, 1/5, and so on. There's another way to do that, and you can actually permanently set MATLAB to use rational numbers, and you should call it format RAT. So format is a function. It's not a function more than it is a, okay, it is a function to MATLAB, but what it does to MATLAB is it changes the settings of MATLAB. So when you go format RAT, it tells MATLAB to use the rational function, the rational format of numbers. And then you do this sequence, sequence equals 1 dot over k, and it automatically does it. But every number that you do from here on out will come out as a rational number. So if you just type in 0.5 and hit enter, it comes out as 1/2, 1/2, right? And if you want to go back to format short, which is one we were using, it gives you the short decimal form. So it's 0.5 and it equals 0.55000. So anyway, that is that. All right. They use the cumulative sum again on page 84. just to show that again. Sorting values. So now we can actually sort values. We get one of these. Let's do another random number array. Let's do random numbers between, let's do one row and 23 columns. Let's do 23 elements. So 23 random numbers, right? It's all these random numbers. And I'm going to sort these numbers now. I'm going to sort my answer. And what it does is it puts them from lowest to biggest, smallest to biggest. Smallest number is 0.0098. Biggest number is 0.9715. You can see how that might be useful in many different ways, I hope. You can also do a sort, and you can change the going from ascending to descending. So I sort answer, but I don't want to sort. Yeah, sure, why not? So I'm going to sort this previous thing that is now my answer. And I'm going to sort it in terms of descending. So sometimes when you give a command to a function, in fact, oftentimes when you are telling a function how to do something, you have to put that command into quotes, single quotes. So I'm going to do descend into single quotes. That happens to be one of the commands that sort knows what to do with, and it changes how sort is done. It changes it from ascending order to descending order, right? So it starts off with the biggest number, 0.9715, down to the smallest number, 0.0098. So sort descend. There are also commands for sorting by rows and by columns, right? So let's create a new, let's see, we already got one. No, we don't. So let's create, they're creating this vector, this matrix, I guess. X equals, and it's 1, 3, and then 10, 2, and then 3, 1, and 82, 4, and 5, 5. So there's our array. Looks like that. It's got 2 columns, 5 rows, looks like 5 rows, 2 columns, right? And we can sort it. You sort X. Then what it does is it sorts it in from the lowest number goes in the first row, first column. The next lowest number goes in the, no, actually, no, that's not what it's doing. It's sorting by column, actually. So again, that's another example of that. We're going to do things by columns if it has rows and columns, multiple rows and columns. So it sorts the first one, the first column becomes 1, 3, 5, 10, 82 instead of 1, 10, 3, 82, 5. The second column, 1, 2, 3, 4, 5 instead of 3, 2, 1, 4, 5, right? And we can force it to sort by rows by using sort rows command. So this function sort rows, I think we'll do it by row, right? So the first row remains the same. Let's see, is that right? Did it do that? Sort rows X. What was X? This is X right here, right? So doesn't look like it's doing it actually. Sort rows, basic values in the first column. Oh, it keeps each row intact actually. So we actually need to have a different matrix to show that. So if we want to do it like this, actually, sort rows X comma 1. So what it's going to do is it's going to base, let's see, sort rows, ascending order on the basis of the values of the first column and keeps each row intact. Right, there we go. So what it's going to do is it's going to sort each row by which one has the lowest number in the first column, right? So that's what it does. So this was our original matrix. Row 1 has the lowest number in the first column, so it becomes the first row down here. And this actually did the same thing. And then row 3 has the lowest number, as the next lowest number, so it becomes the next row, 3, 1. And then row 5 becomes the next one, and then row 2 becomes the next one, and then row 4 becomes the last one, right? And if you do sort rows X1, it does the same thing, but if you do sort rows X2, it's now going to sort it by the number that comes in the second column. So in the second column of X, if we go all the way back here to X, in the second column, we start with 1 being the smallest, and so that one is actually the third row, 1, 3, 1, 3. And then the second one is the next smallest, and it stays where it is because it's in the second spot. And then the first one is the next one that comes, 3, 1, 3, 1, 1, 3 right there. And then the fourth one stays where it is, and the fifth one stays where it is. So does that make sense? It's a little bit weird, but essentially you can pick any column you want and sort by that column, right? And that's something that you can do in Excel. In Excel, you do sort, and then you choose the column or something, and I don't remember exactly what the code is in Excel, but you can do it in Excel, and you can do it other things as well. You're just sorting by a particular row or by a particular column. You can do it by a particular column as well by doing the by using the transverse, the little apostrophe after it as well. So you can do that. Here they do it with some skating results. They have skating results of 5 different skaters, and they sort it by the number of the skater, but they can also sort it by the time of each skater, so that they you know your fastest skater comes in first. And that would, and if you look at the bottom of page 86, when you do the sorting by the second column, the timing of the skater, then you actually get the fourth skater came in first, the fifth skater came in second, second skater came in third, and so on. So that can also be quite useful. Matrix size. We have 2 different ways of doing size of a matrix. So the size of X right now is 5 rows, 2 columns, right? But you can also do the length of X. The length of X will tell you the number of rows. Or is that right? Yeah. So actually, it doesn't tell you just the number of rows. It tells you the largest dimension of the matrix. So if we do the lengths of X prime here, it'll actually tell us 5 as well. It won't just tell us 2. And then you can actually get multiple outputs for size. So if you do the AB thing again, and actually it's just called rows, because normally in MATLAB people call this rows and columns, rows calls. And I set that equal to the size of X, then it will actually assign rows equals 5, columns equals 2. Right? So that's size can output those numbers to variables as well. And then we have numL. This tells you how many total elements are in the matrix X. So that's the number of rows times the number of columns. So that's 10 for this case. Yeah. if you just have a row column, so if let's do this one here. We have K, which is just a row of numbers. So it has one row and many columns. If we do size of K, let's see what that gives us. So it tells us there's one row and 5 columns, but, and then size of X, of course, or size of K prime, let's do. So K, size of K prime, the transpose of K is 5, 1, flips it around again. All right. So that is that. We're all the way through all that. We only have a few more things to learn about. In this next example that they go through, this longer example, they do this weather data example where you have this big chart of data from a bunch of different days in a bunch of different months for the whole year of 1999 in Asheville, North Carolina. They give you a bunch of precipitation, right? And you're going to put that into a matrix and you're going to find the maximum precipitation day and you're going to find the minimum precipitation day. You're going to find out how many days there was no precipitation. You're going to find out the monthly total by adding a whole row together, or the yearly total by adding all the rows and columns together, right? That kind of thing. And it's just using these tools that we've used, that we've learned about, and it's a very good exercise. Again, I don't like to go through them too often because they take so much time, but not a bad thing to look through or to use for practice. It's also a good way to lift code when you need it. If you need to do something like this in your homework, you can come over here and take the code from it. So the examples are a great place to find good code. All right, so now we're going to move on to the variance and standard deviation. These are both statistics numbers. What the variance tells you is it tells you how much a number, it really tells you how much the square of your number is changing from the square of your measurement is changing from what it should be, right? So if you're measuring bags of apples, for example, and the bags are supposed to be 5-pound bags, and you're measuring this bag is 5.5 pounds, well, that one has a variance of 0.5 times 0.5, so it'd be 0.25. It has a variance of 0.25. But a bag that's negative, that's below 5 pounds, 4.5, also has that because it's the square. It has a change of negative 0.5, but you square that to get 0.25. So the variance is the square of how far off you are from where you should be, from the average, in other words, right? So that's kind of how you think of variance. Standard deviation is the square root of that number. So the standard deviation tells you essentially how far you are off from the average. So though both of those numbers can be calculated automatically in MATLAB. They give you the formulas for calculating these on page 93. You do not need to remember those. You don't even need to remember what the variance and standard deviation are technically. I'm just going to show you that it can do it. When you're doing statistics, you probably dealt with the so you've probably dealt with the bell curve idea before, I'm sure, where you have the bell curve of grades in a class, for example, and your teacher says, well, right here is the average grade in the class or whatever, and that's fine. That might be a 75% or an 80% or whatever it is. And the reason for the standard deviation and the variation is because in a natural system, in nature, when you have random elements and so the random elements in a classroom, for example, are the random abilities of the students. If you have a class of 50 students, you're going to have, it's just natural that you're going to have some students that are maybe not as good at what you're doing in that class and some students that are really good. And then most students will be somewhere in the middle. And if that's a natural distribution because of nature, randomly chosen things, random abilities, random whatever, then you're going to get a bell curve of grades very likely. And one standard deviation of those grades in this class is going to cover the vast majority of that class. And that's why we use standard deviation, because it covers like 68 or 67% of the class. If you go out 2 standard deviations, it covers like 90-something% of the class. And then the 3 standard deviations out, it's like 90 something, 97 or 95. And so that's why we use standard deviations. Then we use those standard deviations to determine grades, you know. So this might be your C plus, this might be your B minus or whatever, or maybe it's a half a standard deviation that determines C plus and then B minus or whatever. That's why this kind of thing exists. But anyway, this class is not graded on a curve like that. That's what they mean by graded on a curve. They set up that curve and then they choose the standard deviations and assign the grades that way. I do not grade on a curve. So anyway, going back to what we're doing here, let's close this out. Okay. Standard deviation and variance. The variance is just var, right? So if you have my set of grades here, I don't have my grades anymore. Let's set up some more grades. Woo. So I'm going to set up my grades, random grades thing here again. And if I want to know the variance of these random grades, I just do var of rand underscore grades, right? Whoa, it's a huge number. Why is it a huge number? Because the variation is the square of that thing, right? So if the average number that you're off by in these grades is something like 30%, well, 30 times 30 starts to get up to be a big number. You know, this is like 20 something times 20 something. So the variation in my grades is like something like 20%. And if you want to know what the standard deviation of that is, then you just do STD, which is an unfortunate acronym, right? But that's what it is. STD, and then you do that, and it turns out to be 28. So 28 squared turns out to be 791 ish, right? So you can do the standard deviation and the variance, which is useful, so you don't have to program that into your computer every time you use it. And it's very useful in all of natural sciences. Anything that's studying nature, from studying the way children behave, the number of hours that a child cries every day, to the number of galaxies in the universe that are a certain size or whatever. All of these natural things have a tendency to fit into these statistical probability kind of things. So it's very useful. All right, random number generators, which is, I think, our last thing before complex numbers. So we're not going to really go through complex numbers, but we will do computational notations, but very close to our last thing here. Random number generators. Rand here of 5 creates a matrix that is 5 by 5, 5 rows, 5 columns, and it has random numbers between 0 and 1. And of course, you can actually do random 5. We can call this, and we can give it a name. We can call it A equals random 5, or we can put a negative on it, so it equals negative numbers if you want. You can also do negative and positive numbers, but you have to kind of do it on your own. So let's do that really quick. Let's say that B is going to equal a matrix of numbers that's between -1 and 1. How do we do that? -1 colon 1 will give you a set of numbers. It will give you 1, 0, 1. That's what -1, 0, 1 is what it will give you. Can we set up a set of random numbers between -1 and 1 using this random number generator? I can't remember how to do it. I know you can do it. So I'm trying to think of it myself while you guys are trying to think of it. What do you think? Can we do it? Let's do let's, I can't remember how to do it. I know it can be done. They don't have a function for it, I don't think. I was looking down here on the list of numbers. Mean of 0 minus 1. Well, I suppose you can do it with the rand n. I guess that actually does do it. A mean of 0 and a variance of 1. Yeah, that does it. Okay. So I'm trying to remember what, so the rand n function actually does do this as I looked at it more closely. Rand n of 5 should give us a random, yeah, so it does do negative. So what that one does, so now I know how to do it. No. But what it does actually is it makes use of the variance function in the previous one. So it actually creates a set of numbers where the mean, where the average of the numbers always averages out to 0. So it's centered on 0 somewhere, but there's a variance that goes between -1 and 1, or there's a standard deviation that allows it to go between -1 and 1. So while this set is not actually perfectly random, it behaves as if it's random in nature. Okay, so if you make a big enough set of this numbers and you plot them out on a bell curve, it will actually, or plot them out on a curve, on a graph, it'll actually create a bell curve where most of the numbers are close to 0, and they get increasingly rare as you get to -1, and increasingly rare as you get to +1. So it's a very natural kind of set of numbers, although it's not technically super random. So anyway, you can do it. So those are Gaussian random numbers, we call them. Not universe, not totally completely random. So that kind of gives you a set like that. If you really wanted to make a set of random numbers that is not Gaussian, that doesn't give you that curve, then we could do this. We could do rand 5 times rand n dot times rand n 5. And that would be fairly random. Of course, the Gaussian one is going to still give it a little bit of a bias, but you could also, you could possibly remove that bias by doing a normalization. For example, perhaps we subtract off rand 5 again and add rand 5. That gives it some more randomness that's not so connected to the Gaussian thing. And then all of a sudden we have something that appears much more random, right? But we're still creating random numbers from something that has a Gaussian tilt to it. But you can do all kinds of things like this. And programmers do. This one actually gives us numbers greater than 1. So I actually have I do need to actually normalize these two, which I did. Normalizing means I need to set them to numbers less than 5. So I'd have to actually divide this one by 2 and divide this one by 2 so that I make sure I don't go over 1, if that makes any sense to you. So then they all stay below 1, between -1 and 1 rather. So anyway, just different things you can do. So random numbers, you can generate them. Here they actually do one where they're creating some noise they're creating some noise over a file, over a music file. So music, when you record an MP3, for example, when you copy an MP3 is just a huge matrix of numbers. That's all it is. And the matrix of numbers essentially tells the computer what note to play at what moment in time. That's pretty much what it comes down to. Now, it's not really that simple. It's much more complex than that, because if music was just a simple, huge array of numbers that did that, it would be a file too big to put like on your cell phone, because music has an incredible amount of numbers associated with it. So they use what's called a compression protocol. The compression protocol is actually a function. It's actually a computer program that takes the music and compresses it into a digital format, into an array of numbers that the computer can look at and say, oh, this is what it should have looked like, right? So, and it actually cheats. It cheats by saying, well, this tone is going to be called this number in the matrix. But when it puts it back into that tone, it can't create the tone completely, because that tone is not just that tone. It has a lot more information. So if you play a very low note on a piano or or a synthesizer for some piece of popular music that has a really low bass thing to it, that thing is not represented digitally very easily unless it started out digitally. So sometimes in popular music, for example, a lot of rap music or bebop, or not bebop, hip hop. Bebop is jazz form. Hip hop is a pop form. But in hip hop and rap, there's a lot of bass that's actually computer generated, right? So the bass is almost never a real musical instrument. It's computer generated. So rap music is often recorded with just the singer and not the actual sound. They listen to the sound, but that's not ever recorded. They put that in with a computer so that it sounds better when you play it back. Because if you recorded it, it would actually take something away from it. So rap music and R&B and all this stuff that uses a lot of electronic tones actually comes through better in MP3. If you did jazz music that way, you actually get losses, because you're recording an actual sound, turning it into some digital thing, and then you're returning it into an actual sound on your speakers. And that actual sound on your speakers is not the same thing you started with. It's gone through a program and been processed by a program a couple of times. And so people who love jazz almost never use MP3s or CDs, because you don't get a very good sound. They'll use a record or a tape, which is an actual recording, so they can hear what the sound is actually supposed to be like, right? Classical music is the same way. The classical music, people often love to listen to the record. Even though you get a lot of noise on the record, they like to listen to that. Now, this part here, they're going to actually take some music and put noise on it, because noise is actually random elements. That it's like little pieces of dust on the record, or it's a magnetic, a tape uses magnetism to record sound, but the earth has magnetic fields all over the place. So anytime you play a tape, you're not only listening to the music, but you're listening to the magnetic field of the earth. And so you have this noise in it. That's why we went to CDs and MP3s, because CDs and MP3s, there's no noise. It's just whatever is recorded digitally on there, and that's it. So anyway, you can actually add noise to a music file, to an electronic music file, by adding random numbers to the file. And so that's what they're doing in this example. But you can also remove noise from a file by looking for random numbers in the file. And you do that by creating a wave out of the file. And that wave shouldn't have all kinds of random spikes in it, because random spikes are noise. So that's actually how they remove noise. When you watch an old movie, for example, or listen to an old piece of music, and they say that it's been digitally remastered, that's exactly what they've done. They've gone into the file, they've looked at they've looked at the analog file and looked for all those spikes, or a digital file and looked for the spikes, and they've removed the spikes, they've smoothed them out. But sometimes there's spikes that belong, right? So when you're playing guitar, for example, you play guitar or a drum, there's always that little thing that happens when you slide your finger. It sounds like a little zip on the string, right? Musicians want that in there, because that's part of the music to them, right? Drummers, when you hit the drum, there's a tactile kind of ping at the beginning, and then you hear the drum, so right? And they like that sound because that's part of the music. Echoes in the room when it hits the back of the room and comes back, if you're in if you're in a concert hall or something, musicians like that because it's part of the experience. But so they try to leave those in. Those are random elements that are kind of random, kind of not. They try to leave those in, and they try to extract things that are like, well, the tape was rolling along here and somebody stomped on the floor, so the tape jumped, and then all of a sudden you have this weird random element. And so all of that can be done using computers. They rebuild these wave files and they look for those random elements, and then they just erase them. And then when they build a new digital file, they have the elements that they want. They don't have the elements that they don't want, and you've got remastered music and you can do it with video as well. You can do it with anything really. So that's an application of this, looking at the things that we're learning right now. We're pretty much done. The next section is complex numbers. We're not going to deal with complex numbers much. We don't do complex math in this class. Just know that math can deal with the square root of -1. It knows, MATLAB can. And then the very last part, they talk about the limits of, well, they do talk about special values and miscellaneous functions. We've talked about many of those. I mean, you can call the date. You can actually ask for the date. You can call the time. Infinity, we've looked at. Pi, we've looked at things like that. But also, the limits of MATLAB talk about how big, what are the biggest numbers that MATLAB can deal with? What are the smallest numbers MATLAB can deal with, essentially? And so that, and you can actually ask for those numbers from MATLAB as well. And so those are all there. So that finishes up chapter 3 for us. We're done with chapter 3. So you're going to use all that information that you've learned to work on some problems in the chapter 3 programming assignment. Don't forget to turn in your participation file and also to do your shared document entry, and have a great week. Yes.
For me, go when you introduce the variable
K.
matrix kit.
K was there. Yeah. So K equals 1:5. What the colon does is it creates a matrix from 1 to 5 in steps of 1. And you can also do this one. You can do K equals, I could do K equals 1, 2, 10, like that. And that would create a matrix that looks like this. It would look like 1, 3, 5, 7, 9. So it goes from 1 to 10 in steps of 2. If it goes over 10, it doesn't do anything else. Anybody else have questions? All right, have a great day. Take a drink if you'd like it.
How do you
Thank you too.
How do you change it from fractions to decimal?
Fractions back to decimals. So to change, using format, we did format rat to change to fractions. And then you can go back to format short to get short decimals. That gives you numbers like 0.50000. That's like that, I think. Or you can do format long, which gives you many more decimals. Did you have any more questions? Or?
I'm gonna sit here, but I'll go ahead and finish that grading in the AutoCAD one.
Yeah, I'm going to finish that this week. So.
Yeah, because I'm only out of town before UP will.
Oh yeah, I can do it right now if you want. I can take a look at it right now.
Yeah.
I've got one more question here. Let me take a look really quick. I'll turn off my screen.
That's the one that's with UP, how they have.
Yeah. Yeah, let me get that done for you really quick.
I think it's final.
Oh,
I
shoot.
just get a couple of,
This computer actually doesn't have AutoCAD loaded onto it. I'm gonna have to go to my other computers up at the research farm, but I'll go do that this afternoon.
yeah.
Yeah, no problem.
I'm gonna try to go home and finish that other one. I didn't realize when I sent the message that didn't see it was the 2-part.
Yeah.
So it's like, all right.
Yeah, I'll go take care of that and see if we can get that done as soon as possible. So, yeah, no problem. Sorry about that.
That's no problem. I might, it all depends. I'm gonna try to get it all done by 11 too for the assignment. I might just have to email you to,
Give some more time.
just for tomorrow.
Oh, we can do that just right now, and then you don't have to worry about it.
Yeah, 'cause
For chapter 2.
just chapter 2.
Yeah, we can put that in tomorrow.
There's a chance I'm gonna start typing just.
Fall asleep. No worries. Yeah. It's now due tomorrow at 11.
Yeah.
So
Alright,
go ahead and finish that up.
Look, I think I've been up since about 10:30 or 11 last night.
Been there, done that.
No, that's pretty common.
Yep.
I'll see you next week.
There are probably some little hiccups, because you kind of went like to something a little bit faster than we intended, right?
Let's take a look here. If you ever want me to slow down, just tell me. Just say, wait. If you ever want me to slow down, just tell me. Just say, wait. Tell me what you did there. Just interrupt me. Because I will just continue to go if nobody interrupts me, really. Just got to raise your hand and say, wait, what happened there? And, I'm not going to go through your participation file and see if everything works.
Yeah, here is like 215 lines.
No, I'm not going to go through it and check. I'm just going to check to see if it's there and check to see if you did, you were there for the whole class. That's all I'm going to look for. And then I'm going to give you full credit for being there, essentially. I'm not going to check to see that everything worked right or that, you put everything down perfectly. That's not important to me. So what other question did you have about something? Anything in particular? No, just moving too fast. Yeah, if I'm moving too fast, just say, hey, slow down, slow down. There's just a lot of things to cover, and mostly you're going to learn this stuff just by doing it. So if you're doing it here in class, you're going to learn a lot, even if you don't get it all right. But then when you go to your homework, you're going to learn even more. It's just learn by doing it. It's like learning English, right? Learning English, you learn it best just by speaking it, right? Or
I like
watching
how
TV.
you're, I studied programming in high school, and that's what the career of I kind of like your professor approach, like you're giving us everything, like this does this function does this does this, and then the logical part is gonna come later.
Yeah.
When we need to use that and like shape it to get the program.
Yeah.
And I kind of felt like that when I was studying programming, we were first bombarded with logical.
So were you just in a classroom just listening?
No, yeah, it was kind of like that. Like it's not. Yeah, it was.
You didn't have your computer out doing.
No, I had computer on, and
Yeah.
I was like doing code, but like, especially they say, for example, like he is teaching, like our professors were teaching us how, like they should have like taught us like there's probably a function I can bet.
Yeah,
There's function in C or Java that's like for sort.
just
To
does it.
sort an array.
So they're teaching you
And
theory.
they're like, yeah, no, like you have like a number that's like counting every kind of like that goes through all the arrays. You have a for loop.
Yeah.
Then it goes through all the array, and then how you need to write the code that this looks like if this number is bigger than this is bigger. Like I mean, okay, I understand, but when I think like that, when I become like a programmer and everything, I'm not exactly gonna not memorize all that stuff. I'm just gonna look for a function.
Yeah.
That sorts my array, and I'm just gonna call a function.
Yeah. And the thing is that there are so many different languages out there that some programming instructors believe that they should just teach you the theory, should just teach you the logic. But when you're first learning code, you really just have to learn how to do it. You just have to learn how the functions work, and then you can teach them how to use it, because then they're doing it, right?
Yeah, exactly.
So,
And that's the thing that I kind of always like.
and I'm not a great computer programmer. I'm just not. I'm mediocre at best. And so I can't sit down and have a conversation about the theory of code and the theory of logic. It's just not, it's beyond me. I don't know that stuff. And I don't even want to. It's just something I'm not interested in.
I also don't think like many programmers in today's industry that they are exactly that, like I said, like programming as how I see it and how like people higher level They just know how to manipulate the formulas and everything. This,
Learn
this,
how to-
they manipulate it and everything, but they're not developing everything from ground.
No, not,
That's a lot of stuff.
It's been done already.
Beginner is like intense, it's super intense.
Yeah, I had this, in my first computer class, computer programming class, we sat in a lecture where the teacher just talked at us and wrote things on the board. And I'm like, I got nothing out of it, nothing. And then we had a lab every other day, and I learned everything in lab, so I just stopped going to that class, and I'm like, that's a waste of time. I'm gonna learn it just by doing it. So,
Yeah, absolutely. But we were on a computer that, it was kind of, we would be on a computer and we would just copy what our math teacher was doing on a projector.
Yeah.
Yeah, so.
just
it
copy
wasn't
it,
too bad.
copy it, copy
Yeah,
it.
we were doing it in Python. And then we had to, and we made a game, like we had to make a game. We were using Raspberry Pi,
Yeah, Raspberry Pi,
yeah,
control microphone.
yeah, so we had to make a game, like using it as a controller for
I'm actually thinking of doing a Raspberry Pi device. I was just shopping for some parts. I want to make a box that has a whole bunch of sensors in it connected to a Raspberry Pi, so that it can I can point it at you and it would send a little ultrasound, sound out to you, an ultrasound wave, bounce off and you can tell how far away you are. Or if I moved it, it would tell me how far past I was moving. Or if I dropped it, it would tell how fast. And it would also have things like a force sensor, so if you pull on the force sensor, it would tell you how hard you were pulling, and how hard you were pushing. Have a light sensor, and all these different sensors all in one little box. Because you can buy those things, but they're all separate, and then you have to plug them into your computer. But if you just had one box and it just talked to your computer using Bluetooth, then you'd be done. So I'm thinking of building one. And maybe I'll sell it and make, $10. Hey, what's up? Did you have a question, Logan?
Yeah. How do I upload stuff from MATLAB to where we turn it in?
Okay, so when you're in MATLAB and you're doing code, remember that you want to be opening up a script every time and writing your code in the script. Remember to do that?
Yeah, I did that. How do I upload it though?
So
Or
once
save it?
you've done that, then you've saved it. Then you want to go ahead and take that file and upload that file into MyOpenMath. So if I write some code here, for example, if I say x equals this array, 5, 5, 6, 7, 8, or something like this. And then my next line of code, I'm going to take the mean of x. So that's my code. And if I go ahead and run that code down here, and it asks me to save it, and I'm going to say, this is Jared _ homework 2 or something like this. It's going to save it in these files, in this directory. I can change the directory if I want, save it wherever I want to save it. It goes ahead and saves that file as jaredhomework2.m. And then I'm going to go ahead and upload that file from that directory. And it's sitting right here in the current folder. And you can actually drag it directly from there, I think. So if you go to your homework right here, chapter 2, programming assignment, and then I start this thing and I choose a file like this. So I think, no, I can't drag it from here. So I'm going to have to go from my documents to MATLAB to participation files. And that was the Jared chapter 2 right there, homework 2. And I select that one and I just upload it like that. Then you'd submit. Does that make sense?
I'm gonna be honest. I didn't see half of that because it stopped sharing your screen.
Oh, my screen's. Where's my, I'm sorry. So you saw the part where I saved in MATLAB. Did that make sense?
Yeah, I have it. I have it saved, but I don't know how to get it from here to there.
Let me do the other, let me just open my Firefox, then I'll show you. So I'm going to go to my homework then. Chapter 2 homework, right? Right there. Then I'm going to start the assignment and I'm going to go to choose file for question 1. So there's several questions. There's 2 questions in this one. Question 1 where I do problems 1 through 7. And then question 2 where I do problems 8 and 11 through 14. See that?
Yeah.
So for question 1, I choose my file. I go, it takes me to my place where these files are at, and I choose that file. And then I just submit it, and it will upload that to that spot. Then I go to question 2, and I'll have a different file for question 2, and I'll do that.
So I must not be like saving it to my computer. I think it just saved in MATLAB.
It probably did save to your computer, but you maybe don't know where it's at. So if you go to your in your computer, let's see what's going to look the most like Windows. This looks the most like Windows, maybe, right? So what you want to do is you want to usually go to Documents, and then it'll be in a MATLAB file in your Documents. So here's my Documents, and it opens a MATLAB file there, and that's usually where it will be.
Yeah, I only have IOLab files there. I don't know.
So let's go back to MATLAB really quick. I'm going to share my MATLAB window again. So if you go back to MATLAB, all your documents are being saved in this thing called current folder over here.
Yeah.
So if you go over here to current folder and press this, let's see, what do you have to press? How do you figure out where the current folder is?
I have it down. I can see all my current stuff. So.
Oh, here it is. Yeah, here we go. It's right up here in this bar.
What did you press to get that?
So I have my current folder, and I clicked on my current folder there. And this bar up here shows where it's at. It's under Users, Jared Daily Documents, MATLAB, Participation Files. Do you not have this bar in yours?
No, mine just says MATLAB Drive.
Okay, so open up. Can you share your window with me?
Yes.
I'm going to stop sharing mine. Do you know how to share your screen? It should be at the bottom of your Zoom window. Should say share screen. There
I
you
think
go.
it's this. Is that the right one?
All right, so yeah, yours looks like it's being shared, saved to the cloud, because there's that little cloud to the left of your MATLAB drive on the file. See that little cloud there?
Okay.
Yeah. So it looks like
Yeah.
you're saving to the cloud. Are you using the online version of MATLAB, or are you using a computer version?
I don't know how to download it, so I'm on the online version.
So yeah, okay, so it is definitely in the cloud. To download it, you're going to have to use that little, right next to the new button. Look at that little, yeah, just hover over that. Let's see what that says. Yeah, so go down to the one below. So that should allow you to download this file. So go ahead and hit that. And then go ahead and, yeah, so now it's in your downloads. So you're good to go.
Okay. And then
That's
I can-
actually, so is the online version of MATLAB free?
I do not know. I bought it, but I just don't know how to download it. So
Okay. Do you want me to show you how to download it real quick?
yeah, that'd be great.
Okay. So let's go to your web browser, whatever it is. And what kind of computer do you have, first of all?
I have a MacBook.
You have a MacBook?
Yeah, a MacBook.
Okay. Yeah, so go up there to go to search and open up MathWorks. Yep, that one right there. And did you already create a MathWorks account?
Yeah, I paid for it and everything, so
Okay.
I just don't know.
That's fine. Just go on to log into your MathWorks account, push the little people button there. There you go. That's the one. So you're in there. So there's your license. Go ahead and click on the download button. Yep, that's the one. Go ahead and click on the big blue R2020B. Mac OS, yeah. and go ahead and allow, yeah. Then when that's done downloading, which looks like it'll take a little while, you're just gonna run that file. What's that?
I said my internet's bad.
Yeah, that's a big one. But when it's done, you're going to open that up. And what it's going to do is it's going to ask you if you want to do this with a code or if you want to do it through your MathWorks account. Choose the MathWorks account one where you have to type in your account information again. And then it'll just take you through the process of signing in, and it will download it and set it up on your computer.
Okay.
All right. And if you have any other problems with it, we can talk about it maybe in class tomorrow or something.
Okay, sounds good. I don't know the first one, like I haven't turned in the assignment yet, but like just the one, where we do it together and then we turn in that,
Yep.
the video participation
Yep.
one. I don't even know how I did it the first time, but I somehow downloaded it to a PDF and turned it in that way because I didn't know how. Is that okay?
That's totally fine. No problem.
Okay. Okay. Yeah, I don't even know how I did it, but
Yeah, no
Okay.
worries. No worries. All right, any other questions?
I don't think so. I mean, it should be.
Alright.
Yeah.
All right, well,
Alrighty.
then we will
Sounds
see
good.
you later.
Okay. Thank you.
Bye.
See ya.